Welcome back all of you. In the last class, we started analyzing the proton NMR spectra of some of the simple molecules, which I took as representative examples. Let us now continue further, analyze few more NMR spectra so that you get more familiarity with analysis. Basically, this exercise is to make you people understand what is the splitting pattern, what to look at in a spectrum before you start the analysis. Generally, when you start doing this type of analysis of couple of spectra, you will get a feel for where to see for certain functional groups in the molecule, and looking at the pattern, you should understand what is its immediate neighbor to which it is coupled to, which is giving rise to this multiplicity pattern, and start interpreting that so that you can go ahead and generate a sort of a molecular structure. In the sense, you can start assigning the peaks and get what is the molecule you are looking at. This is basically what you can do in the analysis part. Of course, if you want to get more information, you can even analyze the multiplicity pattern very carefully so that you can get the J coupling information also. That's also possible. But again, we will continue like this with the analysis part. This is a simple molecule. It is the 1S spectrum of 2-methyl-1-propanol. This spectrum is taken from Pavia book, edition 4. Look at this one. This is the structure of the molecule. Of course, look at the molecules, how many types of different protons are there, chemically inequivalent protons. That is the first thing you have to count before you start the analysis. First, we have a OH proton, that's one. We have one CH2 group, which is different because it is attached to OH and another CH here. We have another CH group, which is different from CH2. We also have two CH3s, possibly they are equivalent. Now, we have to start looking at where these protons do appear in the proton NMR spectrum. Let us start from the right side of this molecule, OH proton. Normally, OH protons and NH protons are labile protons. They will generally do not experience couplings so easily. It gives rise to broad hump, especially OH proton gives rise to broad hump. Even though it is attached to the neighboring other group of spins like CH or CH2, couplings are very rarely seen. Not that it is not there, it is there, but you have to take special precautions to do the experiment so that you can see the splitting pattern. So it doesn't matter. But if you look at this spectrum, there is no broad peak you can see here. So OH, if it was there, you would have seen as a broad peak like this. Generally, in all the proton spectrum of several molecules you see in various books and literature, when there is a OH proton, you will be seeing a broad peak like this. But I don't see any of this broad peak here. We have for four different types of protons, we have 4 groups of peaks. That means one of them must be OH. Now, what is this OH could be? If you look at it carefully, since it's not a broad peak, it might experience coupling with the CH2 protons. Quite likely. If it experiences coupling with the CH2 proton, apply 2Ni plus 1 rule, OH has to be a triplet. Sure. Let us look at the spectrum, whether there is a CH3 group. I'm sorry, whether there is a triplet. Not CH3, I'm sorry, it is whether there is a triplet. Of course, there is one triplet here. There is also another triplet here. Triplet-like, not exactly triplet. You please remember, the triplet intensity pattern is 1:2:1. But do they look like that? If you carefully see, it is not a triplet, it looks like doublet of doublet with some extra splitting in the central peak. It will appear central peak is also split. It is not clearly visible here. The only very clear triplets pattern is seen here. So let us assume this must be the OH proton and analyze this and start assigning this one for OH proton. So OH proton is marked C. So this is C. Fine. Next is what? In the same order you come. You will see CH2 here. What is CH2 there? Now the CH2 here is coupled to CH. Okay. And also it is coupled to OH. It has to couple to OH because we have seen for OH a triplet. That means the CH2 is coupled to OH and also the CH. Two individual protons, single protons it is coupled to. Then what is the pattern we expect? This one is 3 bonds away. This is just 2 bonds away. Again, this also 3 bonds away. So this coupling could be larger than this. If that is the case, this proton splits this CH2 proton into a doublet. Okay, this proton splits the CH2 into a doublet. And further, because of this OH proton, this will become another doublet. So doublet of doublet. Where is doublet of doublet here? I don't see. That is why I said this is a triplet. If you carefully see here, this group appears as if it is doublet of doublet. This central peak is partially resolved, not fully resolved, but it is not a triplet. So safely we can assume this must be the CH2. Fantastic. What about CH proton? This is a very complex spectrum it will give, this group especially. Reason is it is coupled to 2 CH3s and also CH2. Remember, multiplicity pattern I explained to you, when one of the protons is coupled to two other many chemically equivalent spins, you worked out the multiplicity pattern. First it is going to split because of this into some quadrates and then again by triplet. So complex multiplicity pattern you are going to see. Look at this one, and that complex multiplicity pattern is somewhere here. So this must be CH proton. Very good. We can analyze that easily now. Then what is left over? So this we have sent for OH, this we have sent for CH2, and this we have sent for CH. Then what is left over? The leftover is only CH3s. And look at this peak, it's a doublet. Why is this a doublet? Even this CH3s may be equivalent chemically, but it is split into a doublet because of the CH. Okay, this CH splits this into doublet, so it appears as doublet. It has to couple. That's what is happening. You can see this CH is coupled to this and also this. Otherwise, it would have been simply a triplet. But in fact, it is a complex pattern here. You must assume it is coupled to this. And when the very fact we have only 2 peaks present here, only doublet of equal intensity, these two CH3s are equal, chemically equivalent, and it should give a single peak. But because of coupling with CH, it is a doublet. This analysis becomes simple, very clear now. We have sent all the peaks. We have looked at the multiplicity pattern, and it matches with our molecular formula and structure given. Next, let us go further. This is another molecule, 2-methyl-1-pentene. Some think it is a linear molecule. Look at this molecule. We will start with this one because it is fairly simple to analyze. CH3. It is coupled to CH2. As a simple reason, you must get a triplet. Okay, that is analyzable. Very fine, we can assign. Then what about this CH2? It is coupled to CH3 and also CH2. This CH2. So what will happen now? As a consequence, this CH2 will be split into a quartet because of this CH3. Remember, it will split into a quartet because of the CH3, and further it is going to be further split into triplet because of CH2O. So this CH2 will be triplet of quartets or quartet of triplets depending upon which coupling is larger. That we have already analyzed. We have a multiplicity pattern, how it comes. We have discussed long back. So what is that complex multiplicity pattern? You see here. This has to be proton B. So A is assigned, B is assigned. Now D. What is D? D is simply a triplet because it is coupled to CH2 and there is no long range coupling. It is simply a triplet. Okay, that is assigned very clearly. You could assign. Now, if you look at that one, there is one group of nearly one peak is there with intensity 3. Look at this one. Intensity is nearly 3. What is it possible? I already told you long back. If you have a single peak of it relative intensity 3 with respect to other groups, it must be CH3 group which is uncoupled. What is that possible? This is the only CH3 group which is uncoupled. So as a consequence, you can assign this for the CH3. That's also done. Now what is left over? Left over is CH2. So this is not coupled to this is not coupled to this is all these things are not coupled. Then what is the pattern you expect? When none of them are coupled, this CH2 has to be a singlet. Okay? But it is not a singlet here. What is this pattern? Why? What is this in making this into a multiplet? Something difficult, to understand. It is definitely not coupled to CH3. Otherwise, this would have become a multiplet. And definitely it is not coupled to CH2 because if you go by that, this would have been very complex. And what is the real problem? Remember, these two protons are not equivalent. As a consequence, it behaves like a 2AP spin system. See, that's what is happening. That's as a consequence of that, this two proton appears as like two protons coupled within itself, strongly coupled. Okay. Well, we can go on interpreting like this. This is the 1H NMR spectrum of butyl methyl ether. Here nothing much to think. Very clearly you can start assigning. It is a OCA3 group, not coupled to any of the protons. It must be a singlet. We can see there is only one singlet here. This is proton D. Then it is not coupled to anything, though CH2 is there. This CH2 is coupled to this. It has to be a triplet. See, there is a triplet here. This is proton E. Then these CH2 protons are coupled to CH2 here and CH2 here. It is triplet of triplets. One CH2 will split this into a triplet. Other CH2 will split each line of the triplet into triplets. So it is triplet of a triplet. What is that possibility? You can see it is only this. Why not this one? See this. You have to carefully observe the complexity. The complexity is much more here. It cannot be simple triplet of triplets. That can safely be assigned to this group because this is split into a quartet by because of CH3 and each line of the quartet is split into a triplet because of CH2. It is more complex than this one. That is why this is assigned to be proton B. You understood the point? This is proton B. Now what is left over? Only this. This has to be coupled to only a CH2 proton and it's a triplet. So this is methyl proton of intensity 3. Very easily you can make the assignment. Now I'm sure you would have got a hang of what to do, how to go ahead in making the analysis of spectrum when the molecular formula is given, when R structure is given. You can think of both. You may be given molecular formula without knowing the structure, but you have to get the structure. That is possible. Because when you synthesize a molecule, do not know what it is. Or you may know the molecule, but you do not know the structure. Either way, you can get either information by analysis of this thing. So we can continue like this further. I will see this spectrum. It's a very simple spectrum. It is spectrum of 2-methyl propanol. Very simple molecule. Look at the structure of this molecule. There is CH3 group, CH group and another CH. Only 3 types of protons are there here. So you get one type of one spectrum, we have one group, another group. Very well, very clear, right? So how do you interpret this one now? Very easy. Simply look at the spectrum. This CHO, where does the CHO will come? Start looking at the spectrum. Where do you start with? Look at the intensity here. Intensity is 6.32. This must be for the CA2, CA3s, which is coupled by this CH proton. Okay, which is coupled by this CH proton and gives rise to, maybe they are very close by chemical shift, which are not resolved, are equivalent. So one peak split into a doublet because of this. If this may not be chemically equivalent because of the structure, then they are not resolved here. If they are chemically inequivalent, we should have seen doublet of doublets. There are two CA3s which are well separated, and each line of this will be doublet because of coupling to CH. I don't, this is a low resolution spectrum, we are not seeing that, but doesn't matter. We'll say there are two CA3 peaks, whether equivalent or not, coming at a single peak. They are split into doublet because of CH proton. Now, what happened to this CH proton? Very interestingly, this CH proton is a very complex pattern. What is this complex pattern coming? This CH proton, remember, is split by two CH3s. One CH3 splits this into a quartet. And each line of this quartet is split into another quartet by this CH3. At the same time, so quartet is 4 lines, 1, 3, 3, 1 intercity. Again split into another quartets. Each line of this quartet is split into another quartet. So 16 lines you have got. Plus this CH proton is also coupled to this CH proton. That is not, there is a coupling between them, because I can see this one. If I look at this one, if the expanded region of this one, somewhere, I don't know where is it. What is this one? I'm not seeing something here. I don't know what is this is written here. Okay, I will come to that, the spectrum of that later, I don't know. Now we will look at this one. This has to couple to this, and as a consequence, each line of this quartet will be a doublet. You understand this? Now we can understand how the spectrum of 2-methyl propanol can be assigned. There is some peak which is coming around 9.6, this one. This is this one, CH proton. It is 9.6 people, correct. Now we know. This CH proton, if you carefully see, is a doublet. Why this is a doublet? Because it is coupled to this. So it is not a mistake in the spectrum, it is the right spectrum. Only thing is I was not seeing carefully. It is this proton which is split into a doublet because of this. So this proton, interestingly, experiences coupling with two CH3s and this CH proton, and interestingly all the couplings are different. As a consequence, you get 4 into 4 quartet. Each line of this quartet is a quartet, and each of them is further split to doublet like this, you can see. So you should get 32 peaks here. That is the reason why it is so complex. You understood the point now? What is happening here? So this is the CH proton. Now the question is, why this CH proton or CHO group, why it is coming downfield? Because it is attached to C double bond O. That's what you should look at in the spectrum. This is a CHO group. This proton is coming downfield, and then CH and to CH3. So there are 3 different groups. You can interpret this fitting pattern very easily. Now, this is the next example. We'll take a few more examples to make you highly comfortable. This is 1H spectrum of ethyl malonic acid. Right? Look at this structure. Very beautiful structure. Perfect symmetry is there along this axis. Along this axis, there is a perfect symmetry. Now, Let us start interpreting the spectrum. How many different chemically inequivalent protons are there? This is equal to this. There is one type. And this is one, 3, and this is 1. There are only 4 types of protons available in this molecule, which are chemically inequivalent. How to analyze that? Very simple. Please look at this one. How do you analyze this one? This CH3 group and CH2 group, very common. We have been analyzing this for quite some time. What is happening in this case? And CH3 and CH2 are present. This is a CH3 group which is split into a triplet because of this CH2. But what is happened to the CH2? This is split into a quartet because of CH3. But it is not just a quartet. What is happening? It is a pentet, you see. How did this pentet come? Because each lane of this quartet is further split by this proton. As a consequence, due to spectral overlap, we have generated the pentet pattern earlier. This looks like a pentet. So this has to be proton B, this one. Understand? Now, this is a side, this is a side. What is left? This one. What is this? This is coupled to this. It has to be a triplet. See? Only thing which is left over is OH. Remember, I told you in the previous spectrum by analyzing, normally OH protons are broad. Why it is broad, we'll explain later when we come to relaxation, etc. It is a broad spectrum we are going to get. So broad, and though any splitting is generally not seen. Of course, here in this case, splitting possibility is also low, no problem. But if there is something attached to that, generally, it is very difficult to see this splitting unless, as I said, special precautions are there in the preparation of the sample where you are going to see the splitting also. But this is safely assigned now. So all the 4 groups of protons are assigned. I hope you are getting the feel for how to analyze the spectrum, looking at the structure, looking at the multiplicity pattern, looking at where do they come in chemical shifts, etc. Okay, this is fairly a complex spectrum compared to previous one. Now, let us analyze this together. What is the possibility here? How many groups of protons are there? Look at it very carefully. This is CH3, one proton. This is one, they are chemically inequivalent. And in between C double bond OCO, so there is a break. And this will not couple to this. There is another proton here, another proton here, and we have a phenyl group. So 1, 2, 3, 4, 5 groups of peaks are there. Count. Yeah, 1, 2, 3, 4, 5 groups of peaks are there. What are the intensities? Here there are 3 protons. We get 3 here, and then we have 2 protons here. We get 2, another 2, another 2, and this is phenyl ring. 5 protons. Intensity is 5. So the relative intensities are matching, agreeing with that. There is no problem at all. Your interpretation comes to interpret which is which, especially the CH2 proton. CH2, this CH2 is also attached to O. This CH2 is attached to C double bond O. Your assignment of this CH2 and this CH2 is something which you have to see carefully. Apart from that, rest is simple. Especially look at these aromatic protons. I did explain to you the case of aromatic ring current when I explained all those protons which are in the plane of the ring generally come here de-shielded and come at low field. That's what I said. That's what is happening. So peak which is coming around this, around generally aromatic protons come at 7 ppm, around 7. So this is this ring. Clear? Now of course this portion is also clear. This is CH2, this CH3 split into a triplet because of this, and there is a quartet which splits into this CH2 split into quartet because of this. Analyzable. Now this is attached to this, and I say this is this CH2. And next is this is CH2 attached to O, comes downfield, and it's a triplet because it is coupled to this. Then this CH2 is coupled to this. So that has to be this aromatic CH2. This is very important thing you have to see. It comes because it is attached to C double bond O. And in case of a confusion, let us say, between this CH2 and this CH2, which is coming downfield, whether this is CH2O or this one. How do you assign? Remember, this is coupled to Ca3. The splitting pattern gives you J coupling. Measure the J coupling. This J coupling should exactly match with this or this. The one which matches with this J coupling, that is the one which is coupled to Ca3. Then you can identify whether that CH2 is this or this. That is another way. You understand? When you have confusion in assignment of the peak, like an example like this, both are CH2s. How do you know which is coming downfield, which is coming high field? Look at the coupling pattern and see which splitting pattern separation matches with this one, and that is CH2. This is the way you can start making analysis. Okay, we are slowly increasing the complexity. We are looking at the next spectrum of the molecule like this. This structure, this formula is known, and this structure is also given, chemical structure. This is the NMR spectrum. Your life has become very simple because everything is marked. In this case, absolutely no need to spend more than 1 minute to analyze the spectrum. Maximum 2 minutes you will get the spectrum. Analysis is simple. You know how? Look at it. This CH2 and CH3 are coupled, and there is a breakage here. You know, coupling, the long range coupling is not seen. They are only C double bond or C1 like this. If you see 1, 2, 3, 4, 5 bonds away, these couplings are not generally seen. So this forms one coupled spin system, and this forms another coupled spin system. So you have to analyze only two coupled spin systems. That's all. No coupling between them. As a consequence, very simple. So what you have to do? This CH3 will be a quartet. I'm sorry, it will be a triplet because of this. And this CH2 has to be a quartet because of this. Where is the quartet here? There's one quartet here. And there is another quartet here. Now the question is, which quartet belongs to this? You have to understand which quartet. You have to now understand, go by the intensity. This is also quartet, this is also quartet. But which is more intense? This is 2 times the intensity. Remember, compared to this. So this must be quartet where this group pertains to 2 protons. Then what it is? It has to be this. This quartet has to be this, which is coupled to CH3. So this is a CH2. This CH2 corresponds to this. This CH3 corresponds to this. Fine, done. Now what is left over? Only this and this. Then this CH3 has to be a doublet because it is coupled to CH. So this is doublet. So this is this CH3. Then what about this CH? Is a quartet. See, this is a quartet. So only thing in this case, whether to distinguish the 2 quartets, which belongs to which, you look at the intensity. This is 1 intensity, this is 2 intensity. See, that is another way of identifying the coupled partners. If you have a difficulty, again, you can measure the J coupling. That's also possible. So these are the ways you can start analyzing these things. Now, more or less, we have assigned all the peaks in this molecule. This is CH31, this is CH, this is CH2, and this is CH34. This is a very fairly simple molecule. In this case, I gave an example because both are quartets. You have to take into account the intensity pattern to identify whether this quartet is belonging to this or this. That's all. That is the only difference here. Rest analysis is simple. We get the coupling pattern, we can do that. This is the next complex molecule. Now I'm increasing the complexity slowly, one by one. Look at this one now. How many groups of protons are there? 6. This is 1, 2, 3, 4, 5, and 6. This is the spectrum. Now start interpreting. Very easily you can interpret. If you look at the spectrum, there are discriminated peaks are there. Very well dispersed. 1, 2, 3, 4, 5 groups of 6 groups of protons are there. But remember, there is a CO, Here one, for if I take this proton H2, there is 1 bond, 2 bond, 3 bond, 4 bond, 5 bonds away. This proton coupling to this proton probability is very low. I don't say this proton can couple to this because there are several bonds away. So that means you can distinguish this is one coupled partner. This is a particular coupled spin system. You can identify this as one spin system and remaining 4 are another spin system. Very easy. You know, you have distinguished two spin systems here. This is easy to analyze. Of course, CH2, CH3, right from yesterday we have been getting triplet and quartet. Now, this has to be a triplet, this has to be a quartet. Which is which? There is one triplet here and one quartet here. This quartet is easily assigned. This has to be this CH2. Now, this CH3. There are two triplets, unfortunately. The reason it could be this CH3 or this CH3, you do not know. How do you assign this? So, we will wait for some time. First, we have assigned this one. That is correct. That is for this CH2. We will go further. Now, we will come to this ring. This CH3 has to be a triplet because of this. Correct. So, now we identified two triplets. Alright. But one interesting thing happens. If you carefully see the triplet separations, see this triplet separation. For this, when it is coupled to this quartet, measure this free J coupling. Measure which one has a J coupling here. This separation and this separation has to match. Whether it is matching for this or this, that identify which is the CH3. Alternately, look at this CH3. This is coupled to CH2. It's a triplet. One of them we'll see later. Come to this proton. This proton is coupled to CH3 and it's a quartet. It is also coupled to CH2. What does it mean? Each line of the quartet will become a triplet. It's a very complex pattern. Why? Where do you see that complex pattern? It is here. Okay. Now the question is, why not this? Why I am asking only, why I am telling it is this one? You will see later. If you look at this proton, this is coupled to this and this, CH3 and CH2, the quartet of a triplet or triplet of quartets depending upon the coupling strength. Whereas look at this one, it is coupled to only two CH2s, this and this. It is triplet of triplets. Triplet of triplets maximum you get 9 lines. Quartets of triplets you get 12 lines. So complexity is more here. So I would safely say this is this CH2. And I would say this CH2 is this one. Now, what is the leftover this CH2 is this one. This is coupled to this. It has to be a triplet. So we assigned this quartet because of this. Now only thing left over is these two CH3s. Whether one is which is 6, that you can assign by making the J coupling measurements. Very easy. You can do that. Okay, either here or there in the multiplicity, this multiplet or this multiplet, measure the couplings, you will know which CH3 is which. That way, you can easily assign. So now assignment has been made, and I said this is 6 and this is 1. And this is, it will be a sextet. And this is a quintet. And this is a triplet. And this is a quartet. So in this molecule, you get triplet, quartet, quintet, sextet, everything you have observed here. Now, if you look at this 5, and if you look at this 6, 5 is this separation. It matches with this separation. That is why it was assigned as 6 by J coupling measurement. Now you got the point. How to make the assignment? It is a very simple molecule. It was deliberately chosen because you have all possible multiplicity pattern you can see except doublet, triplet, quartet, quintet, sextet, everything was observed. And looking at the multiplicity pattern and their complexity and the chemical shifts where it is coming, you can easily assign. Of course, you can use chemical shift information. When this CH2 is attached to this O, it has to be downfilled. That also you can utilize. And this CH2 is standing alone coupled to this. No other coupling, so it has to be CH2. And further it is attached to oxygen, so it has to come to downfield. That way, you can start making the assignments of the spectrum. I hope you all have understood how to make the assignment. So I am going to stop with this analysis. We'll come back in the next class. Let us see how to proceed further. And if I find one or two complex spectrum, I'll show you so that you can get more familiar. And after that, I'll start going to do heteronuclear spectral analysis. First, I'll start with the carbon-13 spectrum. You should know how to analyze carbon-13 spectrum and how to get a good carbon-13 spectrum, everything. And afterwards, we'll go to other topics.